A complex graph will contain at least one of these two properties. A loop, also known as self-edge, or a multi-edge. If I draw a graph like this, for example, a complex graph will contain at least one of these two. Then this is not a multi-edge. Of course, this will be a, first we'll talk about self-edge. This is a self-edge, 1 points to 1. But the edges between 2 and 3, this is not multi-edge. What is multi-edge here is 1 points to 2, 1 points to 2, 1 points to 2, 1 points to 2. That is multi-edge. A multi-edge will have significance most often only when it has a different weight attached to it. 3, 4, 10, 7, 9, for example. Without a distinction between each of these edges, the multi-edge doesn't make sense. A multi-edge can happen in undirected graph also. So 1 points to 2, 1 points to 2, 2, 2, 2. But it will have different values, 3, 4, 10, 5, 9. Three is pointing to 4 nodes is not multi-edge. Yeah, that is not multi-edge. Multi-edges, same direction between the same nodes, multiple edges. Multiple paths is not the right term. Multiple edges. Yeah, or links in the same direction. In the same direction, because here 2 to 3, this is not a multi-edge. Yeah, at least 2 in the same direction. Next is complete graph. Any idea, guys, what a complete graph is? Any idea what a complete graph is? Any guesses? Perfect. Exactly. That is right. So complete graph is there exists an edge between every pair of nodes. There exists an edge between every pair of nodes. So connected graph is there exists a path between every pair of nodes. Here it is edge between every pair of nodes, means every node is connected to every other node. For example, this is a complete graph. A complete digraph is basically the directed graph version of it. There exists a directed edge between every pair of nodes. Means if I draw something like this, this is not a complete digraph. But if I draw something like this, this is a complete digraph. Mark activity has been enabled, guys. Please mark your activity. Mark activity has been enabled. Please mark your activity. And give an example for complete digraph for 4 nodes. Any reason why? You want me to do that? Because you can just extrapolate from this, right? This is 3 graph variation. I already showed you a 4 graph for complete graph. So it's just, put one here, 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 one here. That's it. Yeah, that is right. Please mark your activity, everyone. And then we will take a short break here. We will meet again at 14. We will meet again at 6:14.
Recording stopped. I just start the breakout rooms.
All right, everyone, let us begin with our session.
Recording in progress.
Videos on, face visible. Let us begin with our session. Faster. Videos on, everyone. Faster, guys. Videos on. We'll start. So let's understand how a graph input will be given to you and how you can read it, store it, process it, etc. So whenever you are tackling any problem involving graphs, so the first thing that they will give you is how many vertices and how many edges does it have. Let us take a sample graph like this and we'll use it for the next few problems as well. So please draw this complete graph. Please draw this complete graph. All right. So here, what they'll do is first they'll tell you how many vertices and how many edges are there. In this example, there are 20 vertices and 19 edges. So any graph that you usually deal with online, they have the numbers from 1 to V. So the numbering will start from 1, it will go till V. So if they say that V is 20, means you will have all the numbers from 1 to 20, each number representing one node. That is the usual way that graphs are represented. That graphs are given in the input. So now after that, what they'll do is they'll give you E number of lines. Each line describing U, V, and if it is a weighted graph, you'll also have W maybe. If it is a weighted graph. So for example, let's say first input is 11, 19. So they're talking about this edge between 11 and 19. In that manner, let us write all the edges once. I'm writing in a random order. I think 13, 14 is missing, right? Yeah. So the input will be given something like this. Where you will have E number of lines. If it is a directed graph, then basically U will point to V. If it is an undirected graph, U points to V and V points to U. Now there are two most common ways of graph representations. Can you tell me what are they? What are the two common ways of graph representations? That's right. First way is by creating an adjacency matrix. That's right. The other way is to use a adjacency list. Using an adjacency matrix and an adjacency list. So one thing that I want you all to observe here is nowhere in the input they have mentioned about the node 15. The node 15 is not mentioned anywhere in the input. But that does not mean that node doesn't exist. That node exists. It is just that there is no edge to that node. So when they give you v equal to 20, then definitely, compulsorily, all the nodes from 1 to 20 are present. You should not pick up which nodes are present from the edges that they give. If you do that, you'll miss 15 completely here. Let's talk about adjacency matrix now. So the idea behind adjacency matrix is basically you create a matrix of size in terms of V and D. Yeah, V cross V is fine, but we can simplify and go with V plus 1 cross V plus 1. We don't have to offset anything. We can go with V plus 1 cross V plus 1. Basically, it will contain 1, 2, 3, 4, so on, up to 20. 1, 2, 3, 4, so on, up to 20. Whenever you want to say that I have an edge between 2 and 4, for example, all you have to go is go to row number 2, column number 4, and mark it as true, saying that there is an edge between 2 to 4. And if it is an undirected graph, you should also do it for 4 to 2, go to row 4, column 2, and you should mark it as true here as well. If it is a directed graph, only one will be there. If it is undirected, both will be there. Similarly, if I just want to mark 1 cross 3, then I should also mark 3 cross 1. If I want to mark 2 cross 10, then I should also mark 10 cross 2, and so on in this manner. Something like this, you will keep marking them as true and false. I mean, you'll not mark it as false. It is by default false. You'll mark them as true wherever you have an edge. If it is a weighted graph, then what will change here? If it is a weighted graph, what will change here? Exactly. Instead of true false, you will replace it with the weight of that edge. That is right. You will replace true with weight instead, if it is a weighted graph. If I write the pseudocode for this, it will look something like this. So in your main function, first you will read the number of vertices and number of edges. And then you will create a graph of size. Boolean, we'll go with Boolean first. V plus 1 cross V plus 1. Initialize to false. That syntax will not work. You should obviously initialize it to false in a different way. Once you initialize it to false, now you just have to loop and read those many edges. I equal to 0, I less than E, I plus plus. We need to loop E number of times, right? Or I equal to 0 to I less than E. Then we need to read U, V, and if it is a weighted graph, W as well. Then all we have to do is say graph of U comma V is equal . Don't do this for directed graph. For directed graph, only U comma V will be there. You will not do the reverse. Last 30 seconds. So what is the main disadvantage here, guys, with the adjacency matrix? What is the main disadvantage? Perfect. Space. If unless you have a complete graph or nearly V number of edges, you don't really use a lot of space in the adjacency matrix that you are creating. Or V square number of edges to be precise. So it is pointless to write an adjacency matrix for most of the graphs that you deal with, because of the extra space that is left over. So space wastage. That is one problem. There is also another problem with the adjacency matrix, which is if you want to loop on all the neighbors of 3, for example, then you don't know which are the neighbors of 3. You need to visit 0, 1, 2, 3, 4, 5, 6, 7, 8, so on till 20. If you want to visit all the neighbors of 3, for example, then we visit all V columns, even if it has only one neighbor. But you don't know that it has only one neighbor. You will visit all the columns. So it is not exactly giving you good performance. because of this reason. But it is good at one thing. Can you tell me what is it? What is the major benefit that you're going to get with adjacency matrix? Accessing, that is right. Direct access, exactly. We get direct edge access. You get direct access to any edge you want because it is a matrix. That is a big benefit for adjacency matrix. These are the disadvantages. So to cover up these disadvantages that it has, we come up with the next type of graph representation, which is an adjacency list. Maybe I should write a bit closer. Yeah, that's better. Let me just scroll up and get the input down. So using an adjacency list, the way it works is basically first you have 11, 19. All you have to do is go to 11 and add 19. Go to 19 and add 11. 319, go to 3, add 19. Go to 19 and add 3. In this manner, I want you all to fill this entire adjacency list for this example that I have. One, 10, 10, 1. Last 30 seconds. We will use this adjacency list that we have written here for the next 1 or 2, 3 problems as well. So here, so I hope now you get the idea. So this is basically an array of lists, something like that. So this representation that I have, this visual representation that I have in front of you, the simplest way to create it is I'll write the syntax in C++ and Java separately. And Python, I think it will be implicit. You can easily convert. So one way to do it is you can declare a, what do you say? Vector of int in C++. So this is a vector, and each of these is a vector. Vector is the array list in C++. So it is like a list of lists in Python. In Java, you can do array list of array list. Of type integer. You can do this in Java, but the syntax will get very long and lengthy, and you will get tired writing code in this manner. Dot get every single place. Whereas in C++, you can just do I, J like this, which you can't do it in Java. You should do dot get of I, dot get of J. So what I recommend is, okay, before that, I'll show you what other ways are there as well. In C++, you can also do vector of type int G of size v plus 1, creating an array of type vector. Instead of vector of type vector, we can do array of type vector. Yeah, Dikshit, I'll come there as well. And in Java, actually, that is the preferred method to do it. I can create a array of type array list. Then my syntax will become simpler. So as Dikshit suggested, we can do something like a map here, a map of type int comma vector. Integer will be the 0, 1, 2, 3, whatever index is there here. And the vector is the value int. So in Java, it is basically hash map of integer comma array list. If we can do that, then we can also do map of int comma. Instead of vector, we can make it a instead of vector, we can also make it a not pair. Pair will come later. We will talk about weighted graphs in a bit. Not array. Array doesn't make sense. You can't have a fixed size array there, right? Set. Instead of vector, this can be a set, right? Each of these can be a set. So it will become something like hash map of type integer comma set or hash set. For just the sake of completion, I'll just show you in Python as well. Python, you will do something like I'll do live coding in Python so that you'll understand better. Python, the code will be a bit lengthier. It's not just as simple as showing you the declaration. So now here, guys, out of the methods 1, 2, 3, 4, which method do you think is the most recommended or most best one to use in regular scenarios? That's right. 2 is the best to use in Java. But you don't have to go with 2 in C++. You can go with 1 also. That is fine. The reason why using a map is inefficient or is not ideal is because it is inefficient compared to an array. So unless you have a problem that demands you to, have a map and you do something else with that map, maybe do some map of type set, something like that. Unless you have a very specific scenario, using a map is always going to be inefficient and when compared to using an array. So using an array of type array list is the most recommended way in Java. And you can just go with a vector of vector in C++ because syntax is simpler already in C++. These are the most recommended ways to do it. If you were using a weighted graph, or if you had to create a weighted graph, for example, then what would you change here, guys? What will change here? You need to store the weight along with the numbers, right? Into pair. A class in Java. That's right. You can create a class pair in Java, or you can use the pair inbuilt class in C++. So this integer will now become a pair. It is basically going to be a pair of element comma weight. And instead of set, this can become a map, maybe in that case. A set of pairs is basically a map. So that is only if it is a weighted graph. Let me quickly show you how to do this in pseudocode. Main, you will read v comma e. Then you will declare some. I will show you the code in Java here because it's a bit tricky in Java. Array list, an array of type array list. If you notice, the syntax here doesn't contain what is the type of data that I'm storing in array list. Because you cannot do that here. This is not a declaration of array list. You're not defining your array list here. In this line, you're defining your array. Array will contain array list. That could be any type of array list. But this array is going to contain an array list. That is what you're declaring over here. You should not write integer like this in brackets here. What you should do is, you should loop and initialize each index. I equal to 0, I less than v plus 1, I plus plus. And you will say that g of I is equal to new array list of type integer. Here you will mention that I am going to store integers here. You cannot mention the type over here. You should mention the type in your as a part of your initialization. In C++, you don't have to, go through all this effort and everything. You just declare it and it works out of the box. And after this, we'll obviously loop I equal to 0 to I less than E. And then we will read U, V. And if it is a weighted graph, we will also read W. Then all we have to do is say G of U dot add V and G of V dot add U. And if it is a weighted graph, instead you will say G of U dot add new pair of V comma W. That pair class that you create should accept these things in your constructor, element comma weight, and you will assign them in that object. G of V dot add new pair of U comma W. If you are writing in C++, this will simply become vector of integer G of size V plus 1. So I'm initializing my vector with a fixed size. It is similar to declaring array of type vector, similar to that. If I don't give that size, then you should do dot append every time in your, you should do a loop again like this, which is not really required if you declare it with this size. Then you can skip this step in C++ and you can go here directly. Dot add will be dot push back for us. If you are declaring a weighted graph in C++, then this will become vector of pair of end comma end. If it is a weighted graph, this is a pair inbuilt class in C++. Then what you can do is you can just do G of U dot push back You don't have to do new pair, or you don't have to use the make pair function that is there in C++. You can directly use the curly brace syntax. If you use the curly braces syntax, it will convert it to a pair automatically. So this will convert it to a pair automatically in C++. We'll move on to the next question in 20 seconds. Okay, moving ahead to the next discussion. For the next discussion, it will be great if you're not browsing Instagram in the middle of the session, Prem. I can see it in your reflection of the glass. Yeah. So for the next discussion, let's now focus on graph traversals with a simple problem. Given an undirected unweighted graph and two nodes S and D. Check if we can reach destination from source. Check if we can reach the destination from source. To understand this question, let me just bring the adjacency lister down from the above discussion. We will use the same adjacency list for this discussion as well. So basically, let's say I want to know if there is a path from, let's say, source is something like 3 and destination is something like 7. Let's say I want to know if there is a path from 3 to 7. How can we solve this problem? Using what can we solve this problem? Thank you. That is right. We can either use a BFS or a DFS. a breadth first search or a depth first search? Breadth first search or a depth first search? First, we'll focus on using depth first search. Depth first search to solve this problem first. So the idea behind depth first search is basically you start with 3. Then you will loop on the neighbors of 3. Neighbors of 3 are 19, 9 and 2. First you'll visit 19. Then you loop on the neighbors of 19. What are the neighbors of 19? 11, 3 and 20. So you'll first go to 11. Then you loop on neighbors of 11. What are neighbors of 11? Only 19. But we should not visit 19 again, right? Because we visited 19 already here. We should not visit it over here. Means we need to keep track of the nodes which we have visited in a exactly Boolean visited array. We need a Boolean visited array, which will help us keep track of which nodes we have already visited. Based on the visited array, I'll know that, okay, I have visited 19 already. I will not visit it again. Now I should visit other neighbors of 11. No other neighbor is there for 11. So I will backtrack to 19. 19, what are the remaining nodes? 3, already visited. 20, okay, we can go there. 20, 19 already visited, no other neighbors. Come back. Then go to other neighbors of 3, which is 9. 9 points to 3 again, don't visit. Then go to 2, 2 points to 3, don't visit. 2 points to 10, you visit. And so on. And so on. So you'll try one method. If it is not working, you'll backtrack and try the other method. Whenever I say backtrack, I know your heart will shiver a bit, but don't worry. I am kind of confident that you are good with recursion. Means you're good with backtracking to a certain extent. So we can just write the code for it very easily. It's not like true backtracking, maybe a bit. But I'm confident you'll be able to write code for this very easily. So let's try writing the code for this. We need a Boolean as the return type, because we want to know if it is possible to reach the destination or not. So it will return true or false. We'll call our function TFS because it is DFS. Then we will pass our graph. I am not mentioning the graph type here. I'm putting a dash here because depending on the language and depending on which way of declaration that you're following, you will declare it in that way and pass it. Vector of vector, array of vector, map of vector, whatever it is. I'll just put a dash for the graph type. We'll pass the graph and what else will you pass? You should pass the exactly source and destination. You should pass the source and destination. That is right. Along with that, we should also pass the visited array. We need to also pass the visited array, which will keep track of which nodes we have visited already. Which will keep track of the nodes that we have visited already. Tell me, what is the base condition here, guys? What should we check first? Yeah. You can do source equal to destination first. Great. If source equal to destination, return true. What else should we check? No, that is not a base condition for us. This has edge or not. Visited or not, exactly. You can do visited check either before calling the function or in the base condition. Anything is fine. I am writing it in the base condition because I like to think like that. Visited or source, if it is true, then return false. You are visiting the same node again. Otherwise, what should you do? What should you do otherwise? Check for neighbors. Yeah, we'll come there, but we should do something before we check for neighbors. Perfect, Mahesh. That is right. That is right. We need to mark the current node as visited, and then we will visit the neighbors. So the idea here is S has many neighbors. We'll call it A, B, C, D. S has many neighbors. If you know that any one of these neighbors can reach destination, if you know that there is a path from your neighbor to destination, then obviously there is a path from source to destination, right? So if you know that your neighbor can reach destination, then you know that your source can also reach destination. So for each neighbor of, I'll just write me. For each neighbor of graph of source, for each neighbor of graph of source, if there is a path from exactly neighbor to destination, then it means that there is a path from source to destination. Otherwise, after you check all the neighbors, you can return false at the end. You can also move this visited equal to true check inside here instead of in the base condition. You can say that if it is not visited, visited of neighbor, and if there is a path from neighbor to destination, you can write it like this as well. What is the time and space here? What do you think will be the time and space here? There is no N here. We have V and D. What is the time and space here? V comma V, V into E. V comma V. Space is V for sure, because we are using a wasted array. It will require a size V, or V plus 1 to be precise. But time is not V. See guys, it's not just dependent on number of vertices, right? V plus E, perfect. It is dependent on number of vertices and edges. If you look at our logic, basically, we are visiting every single vertex exactly once. And also we are visiting every single edge exactly once using the loop. So we visit every vertex once, every edge once. Every function call is visiting a vertex. Every iteration in our loop is visiting an edge. And we need V space for visited array here, obviously. Graph is nothing but adjacency list. That is right. Adjacency list is what is storing the information about our graph. I didn't write anything. Okay, this is the function, question, that's it. Given an undirected, unweighted graph and 2 nodes, check if we can reach destination from source. Yeah. So now that I showed you how to do DFS, can you do BFS? So what is BFS? It will look something like this. First, you are at 3. Then you'll visit all the neighbors of 3 first. Then you'll visit all the neighbors of 19. 3 you will not visit because it is already visited. Then you'll visit all the neighbors of 9. Then you'll visit all the neighbors of 2. Then you'll visit all the neighbors of 11. Then you'll visit all the neighbors of 20. Then you'll visit all the neighbors of 10. And so on. What does this look like? What does this look like? Level order. Exactly. We already discussed when we were discussing level order, right? Level order is nothing but a breadth first traversal. And that is exactly what we are doing here. First this, then this, then this, then this. So you basically have to maintain a queue. But here our queue can be simply a queue of type integer. Exactly. Here queue is of simply of type integer. There is no type node here. Okay, finish this code. Let me know once you're done. Breadth first search. You wrote level order traversal at least 2-3 times if you solve the assignments. At least 2 to 3 times, I'm sure. So it should be easy for you. We will pass visited array in the parameter. It is not required. You can declare it inside the function also. But it is helpful in one more problem. I'll tell you later. Finish BFS. Let me know once you're done. No, it is not recursive. It is a queue. So you'll remove element from the queue. You will loop on all the neighbors and add them to the queue. All you have to do is take care of marking visited properly. And checking visited, obviously. The code will look similar to the level order code that you wrote. But instead of left and right, here you will loop on all the neighbors. Remove element from queue, loop on neighbors, add them to the queue. Take care of checking and marking visited in this process. And of course, check source equal to destination also in the process. Just say done in the chat once you're done. Done. Um, Done. I'm just showing you how to do it in Python over here. And this code you can convert to any language of your choice because the code will look almost similar. Oh, Q in Python, right? Maybe I'll use that. Okay. So basically, we will declare our queue. The queue will contain initially S. Queue is not needed actually. How are you doing it without a queue? How are you doing without a queue? You're using a list. List will time out in Python. So pop from the beginning will be linear time operation internally, and it will time out. Pop from the ending is usually fine, but pop from the beginning is a linear time operation usually. Okay. In fact, this will also time out, but let's see. So while should we use len of q? Does q has any dot size or anything? In Python? Doesn't look like that. Yeah, looks like I should do len. After all. Yeah. Len of q not equal to 0. As soon as I write len of q in the while loop, I know it is going to time out, but it's okay. We'll continue. Current node is equal to q dot. Sorry, I'm new to syntax in Python for q. So I'm just searching on Google for everything. Q dot remove. Okay. Oh, it's not remove. Come on. Pop left. Okay. Pop left. Q dot pop left. For each neighbor, we'll call the neighbors as x for x in graph of S. I shared the link with you guys in chat. If you are not interested in looking at this Python code, you can try writing the code for it in whatever is your language of choice. I'm sharing the link once again in the chat. And please finish coding it right now in the session itself. Don't watch it like a Netflix series. You will not understand by looking at the code. You will understand only when you write code. Thank you. Graph of current. Exactly. We need to loop on the neighbors of current, not neighbors of source. That should be graph of current. If X is not visited, or if X or visited of X, if not visited of X, yeah. If not visited of X, then we will visit it by adding it to the queue. Visited of X equal to true. Q dot append X. And at the same time, you could probably check, right? If X equal to destination, return true. Otherwise, you just return false. Let me finish the remaining code. Def main. Come on, guys. Start coding. Start coding. You need to finish this problem today. Do not exit the meeting, even if it is 8:15, 8:20, until you're done with this simple graph code. Insert last instead of append. Is it? No, I think append is working here. Append insert element at the right end. Yeah, append works here. All right, def, test cases, right? For underscore in range of int of input, print test case with hash dot format score +1. Yes and no. Okay, that will come later. First, we need to declare a graph. This is the important step for Python users. You need to pay attention here, how to declare a graph in Python. So basically, I want a list of lists. So what I'm doing is I'm using list comprehension here. List for I in range. Oh, I did not read V and D. First, we need to read V and D. V, comma, E is equal to map of in, comma, input dot split in range of V +1. So do you see what happened here? So I created V +1 number of lists inside this list. So what I did is basically, and so on in this list. And then I can just append into it. So what we'll do is, and remember that there is a wrong way of doing it, guys. If you write it like this, for example, using, that's what I'm trying to point out to you, using the star syntax into V +1, something like this. If you do something like this, guys, it will not work. That is because it will create V +1 occurrences of the same array. V +1 occurrences of the same array means if you push into index 0, then it will push into index 0 of that array. So it is basically pushing into index 0 here, 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 here. If you write it like this, then you're creating the exactly different references of the same array, or basically different insertions of the same reference to the same array. So don't do it like this. Wrong. This will work for integers and strings and other things, but not for arrays. Okay. Then what we have to do is we need to, for I in range, we'll loop e number of times to read all the edges. UVW, okay, there's no W, V is equal to input dot split. And then if BFS, or I can do a ternary here. Print BFS. Oh, I should also create a visited array over here. Visited of size v plus visited is equal to false star v plus 1. BFS graph source destination and visited array. Print yes, if else no. I think that's it. I don't have values to unpack. Oh, I did not read the input properly. Yes, there are Q number of queries. I mixed reading edges and reading queries into one thing, which is incorrect completely. And I didn't even update my graph, which is even worse. Which we'll do first. Graph of u dot append v. Graph of v dot append view. Size of array list is 100 in Java. Do not give a size to array list. And definitely do not give fixed sizes in any code ever, unless it is a TP problem and you know the constraints. And you're writing a memoization code, not tabulation. Then we need to read number of queries for each Q in range int of input. For each query, we need to do this. This is S, D. Let's see how it goes. Okay, done. And if I submit, what will happen, guys? No. Okay, it's saying wrong answer for some reason. Yeah, expected answer is TLE. It giving a wrong answer is not typical. Hey, how did we miss this? So now we will get timeout error. Oh, we didn't get timeout. Great, guys. Python is working. Awesome. So, I mean, I was very skeptical about writing a length of Q here, but it turns out that it's not that bad, which is good enough for us. So who all are done Java, C++, Python? Do it right now. Once you finish it, then I have two small announcements to make, which are directly related to concluding the batch. And also I'll tell you what is the plan for next week and everything else. Session is not done, so keep your videos on. You need to finish that code right now. Don't skip it. Don't be lazy. Don't procrastinate. Do it right now.
Recording stopped.
I'm pausing the recording so that whatever I'm scolding you doesn't go into recording, so that when you're watching the recording again, you'll feel bad about yourself. I don't want you to feel bad. If you need help, just say I need help or something. I will immediately help you. I will look at your submission and I will help you out instantly. If you want, I can show you the code in Java as well. If you need help or something, I will. Done in which language? When you say done, please share the language as well. Python, great, awesome. Try doing depth first search once you're done with breadth first search. Java done, great. Is using graph class better in any way, Python? No. Python, if you declare a class, that is instantly 30% reduction in performance. So if you can do something without using a class, you should probably do it without using a class. Okay. V and E, right? We want to read a number of vertices and number of edges. If you're done with BFS, please do DFS, guys. But let me know as soon as you're done with BFS and in which language you have completed it. ArrayList done in Python. Okay. New ArrayList of size plus 1. I equal to 0, I less than v plus 1, I plus plus. Graph of I is equals to new array list of type integer. Then we need to read E number of graph of, obviously we should first int u is equal to next int, v is equal to next int. Graph of u dot add v, graph of v dot add U into Q for loop. Done Python. Good going, good going. Once you're done with BFS in Python, please do depth first search in, BFS in any language, not just Python. Do a depth first search after that. And if you are familiar with more than one language, try doing depth first search in another language, just so that you're familiar with the syntaxes. And s equal to d is equal to, okay. Then we need to do BFS. We need a visited array, obviously. Boolean visited array of the b plus 1. By default, it's initialized to false in Java, so we don't have to worry about that. Graph as the visited. Then system out println. Yes. Done Python. Good going, good going. No. Static void, Boolean BFS ArrayList graph source destination and Boolean visited. Q of type integer Q is equals to new linked list Q dot add, and obviously mark it as visited. And whenever you mark it as visited, you should also check if s equal to d. While not Q dot is empty. DFS done in Python. Good going, Vishnu. Good going. That's really fast. And current equals to Q dot flip pole to remove it. For each neighbor of graph of current, not graph.get, we should do graph of current. For each neighbor of graph of current, if that neighbor is not visited, then we will visit that neighbor. And we will add that neighbor to the queue. And at the same time, whenever you mark visited, you should also check if it is matching with destination. Return false, run. Object cannot be converted to integer. Object cannot be converted to integer. That's a problematic situation here. We should probably do this. Object cannot be converted to integer. I guess so. Line number 12. What is wrong in line number 12? Okay, it's saying object cannot be converted to integer here. Is it blaming current? Probably not. Yeah, I have used it. Oh yeah, it worked. So I just have to mention the type over here. Because I did not tell which type of data is there in the graph array, in the parameter, it didn't understand and it was saying it's an object and all that happened. Oh, I didn't write test case print statement. Then I can use this. Then I should do t is equal to 1 system out println test case number plus e. Run. T plus plus. Run, successful, submit. Done. Keep your videos on, guys. Please let me know once you are done. Once you're done with BFS, please do DFS. And update me in the chat once you're done. Done in which language, Hare Krishna? Python, okay. Done in Java, okay. DFS is done in Java, great. Done in Python, nice. If you are struggling, please let me know. That is why we are doing it in the session here. DFS done in Python, okay. BFS done Python, okay. So if you are doing in one language BFS, try doing the DFS in other language if possible. If you feel confident about other language. Done using Java, okay. BFS done using Java. If you're done with both BFS and DFS, you can try other problems in page 18. So that you are not wasting your time at least. Please ask me if you need help. BFS done in Java, great. Yeah, got it. Raju, you should not do a loop to append everything into the queue like that. GS Raju. Your queue append will be done inside the while loop. You should not push everything directly like that. Tarun, submit. I will check. Yeah, got your submission. Checking, Tarun. Tarun, this should not be V, right? This should be V plus 1. Because you didn't initialize your last index. It doesn't have an array list and it is saying I cannot do that. Yeah, that's it. And you're missing a colon in your test case print statement. Done. First measure of syntax in Java. Great. That is a bit annoying syntax. But yeah, you finished it. Great. BFS, DFS done. Java, okay. You can try exploring the next problem, connected components problem, so that you're not wasting your time. BFS done in Python, okay. Queue and priority queue are not the same thing, right, Mahesh? Although it works. BFS, DFS done in Java, okay. Okay. BF is done in Python. Okay. All right, 2 more minutes, guys. After that, you can continue solving. But after that, I will discuss about a few things which are important. Okay, focus here, guys. Video's on. Focus here. DF is done in Python. BF is done in C#. Great, great. So, guys, firstly, there is a form that I want you to fill. And secondly, next week's plan. So next week's plan is something like this. Next week, Saturday, we will have session as usual. We will cover graphs and we will cover a few problems in graphs and everything. Next week, Sunday, we will have a lab session instead of the session. Lab session will not be in the morning timing like we had. Lab session will be in the session timing next Sunday. And that will be the final lab session that you are going to have. So this is the plan for next week. Next week, Saturday session as usual. Next week, Sunday lab session, which is the final lab session. Instead of session, we are having lab. Sunday lab is not going to be in the morning time. Sunday lab is going to be in the session time. Depending on our discussion, how it goes and what happens in our next Saturday, we will decide what is the timing of the lab that is required. You are getting exhausted with 2 hours lab, so obviously I'll not keep 4 hours complete lab. So I will plan according to what we will discuss in on Saturday, how it happens, what is the content progressing. If we were able to finish everything on Saturday, okay, great. Otherwise, some 1 or 2 problems might overflow onto Sunday. Then we'll discuss that and then you'll have a lab. Something like that will happen. But we'll discuss everything next Saturday. But I'm telling you that it will not end on Saturday itself. Sunday also, we will have a short lab or overflow content if required. Yes. If it is content, it will be recorded, of course. But if it is lab, it will not be recorded. Okay, this is the plan. And next is I have shared a form with you in the Zoom chat. I want you to fill this form right now. But before you fill that form, please mark your activity. Let me enable your mark activity once. Mark your activity first, and then you can continue filling the form. I did not enable it yet. Give me a second. Yeah, I have enabled mark activity now. Please mark your activity and please fill that form. That form has 4 pages. And it will take you 5 to 10 minutes to fill the form.